It's exciting to join this conference. Today, I'm from Alibaba Cloud Container Service, ACK. Today, I get a chance to present deep learning and genomic computing acceleration with Alluxio and Kubernetes. So let's go through what we have today. So why we need to put the Alluxio on the Kubernetes. Then I will try to give some brief background for the ACK, and we will introduce some challenges for the Alluxio on the Kubernetes. And we have a couple of the contribution, and last time I will introduce some of the best practice to run the deep learning on the Kubernetes with Alluxio, also for some HPC workload. Today, from the recent 2 years, we saw more and more stateless application running on the Kubernetes, on the ACK. Today, we saw more and more stateful set application like a database, like Redis, MySQL, etc. Go to the Kubernetes, go to the ACK. Go further, we saw more and more deep learning workload and streaming workload and HPC workload running on the Kubernetes. So today we provide some tools to help the scientists to build their model using the Arena and the Kubeflow. So you can easily to training your deep learning models on the Kubernetes. We can saw today we have a more data-driven application running on the Kubernetes. But today we need some unified orchestration layers for the data access. And we saw more and more fast growth to the community. And we also can see the distributed computing and storage is becoming the new trend today. Lastly, we see today's when you run your application on the Kubernetes, we still have some bottlenecks. So to access remote data, to access the object data, object store data. As a couple of the presenters today to present the leverages Alluxio to access S3 object on the AWS. On the Alibaba Cloud, we also have a similar object store. We also leverage Alluxio to access the object store OOS. For ACK, it's like Amazon EKS, so we build the managed Kubernetes over the ICE. And we also build a serverless Kubernetes over the ICE. So a user can easily just migrate their Kubernetes application to the cloud. So today we have the challenge here, how to deploy Alluxio on the Kubernetes easily. So we saw we have a couple of the components there. We have a master, worker, and a fuse, etc. So how to scale out this cluster easily. Secondly, how can we run our existing workload on the Kubernetes without any change? As you know, so today we already have more and more workloads already running on existing ways, so it don't have to change anything. So how can we run such kind of a workload on the Kubernetes and you use some feature of the Alluxio? How can we achieve the best performance of the Alluxio on the Kubernetes? So we have three kinds of the challenges today. So how can let's see. So firstly, so we just leverage ham and operator to assemble the Alluxio to make sure that we have one click to deploy the Alluxio master, worker, fuse to the Kubernetes. Secondly, We already, lots of the applications running on the Kubernetes is POSIX driven, so how can we leverage the existing, so we leverage the OOS Object Store Service as UFS, and we leverage the Fuse to provide the POSIX access for the application. Certainly, so we don't need to load data directly from OS. We hope to have the lazy load. Certainly, in order to make the Alluxio running fast on the Kubernetes ACK, so we have to optimize the OOS SDK, it's the Object Store SDK. So we can leverage some short circuit to make sure so that every data can be accessed very fast. Okay, this is architecture for the Alluxio Kubernetes today. So you can see we build the different pod for worker, for master, and we configure all the properties as a config map. On the bottom line, you can see we have built the Alluxio Fuse pod to for the cluster. So once we have all kinds of the components, so our existing workload can running over the Alluxio smoothly. So just to give at the first try, so we just give the different kinds of the OS SDK to load data to the Alluxio. You can see the first time using the OS Fuse, it takes 40 seconds to load the 143 gigabyte data. It's very slow. So after we change the SDK, so we contribute the client to Alluxio. It can just take 2.5 minutes to load 143 gigabyte to the Alluxio. So it's really faster to just speed up the training workload. Okay, so just give you a glance how to deploy the Alluxio on the Kubernetes today. So you can see you just have a few changes for volume 5 here. You just can change the properties to give the different kinds of configuration for this Alluxio. For tire store, so you can easily define the meter type and especially for the quarter, etc., ratio, etc. So use this approach, just using a few changes, you can deploy the Alluxio to the Kubernetes. So it's customer-free and simple to deploy, and easy to share through the Helm repository. So today it's shared on the ACK Helm repositories. Also can be shared on the other repository. Next steps, we just hope to move this Helm chart to the operator approach. Okay, just give a glance how to leverage the OSS. So it's you just can set the access key and the key secrets like S3. So it's sets down. So you can just push it, install this Alluxio to your Kubernetes. So in order to speed up the loading data from the OSS, so you can set the thread in parallel to load the data here. So because we have machines who have 54 CPU over there, so we just give the 54 parallel. Okay. So secondly, so we have a lot of the HPC workload, like the genomic computing, etc. So running on the Kubernetes today. So why we choose Alluxio? Today we have a couple of the things. We have the OSS Fuse directly to load data to the cluster. We also have a CPFS. It's a parallel file system, so it's really fast. It's good performance, good scalability. but it need additional explicitly copy, so user does not like it. We don't need to load data each time. The important thing is this infrastructure is expensive, so you need to spend additional ECS, additional machine to set up this parallel file system. So we go to Alluxio today. So it gives good performance, good scalability, lazy load, and cheap. So you can just reuse existing cluster to power it. So as I just mentioned, so we have Arena tools. This tools is an open source. It's a project of the Kubeflow today. It allows you to run the TensorFlow training in parallel in the Kubernetes cluster. So it's support the MPI or reduced way. It also support the parameter server side of the training. So using this approach, we hope to speed up this approach to training the TensorFlow model. Okay, just to give a look how can training a TensorFlow model here using the Arena here. So the lines in red is just a one-line change here. You can see we just put the Alluxio directory instead of the existing parameter. So you don't need to change anything else. So you can just run this deep learning job over the Alluxio. So let's take a look at the result. So if we're using the previous catch utility, OSS monitor, OSS gateway, it just have the 3,000 image per second. If we're using the 32 GPU here, so if we go to the Alluxio way, we can process 7,900 image per second. So it's amazing. So improvement here. So after we leverage this cache layer, this new cache layer. If you're using another utility is Alluxio is OSS Fuse. So we can see it also have the 50% improvement here. Okay. After we talking about the deep learning workload, so we have another HPC workload as well. So it's we just running our genomic computing on the Kubernetes. We also leverage the OSS for storage for intermediate storage for the processing. So today we also can leverage the cloud native cache Alluxio here for reference data. So the reference data is huge also. So it's about the 60 gigabyte. So it has been reused many times in the workload. So let's take a look at what's the I/O feature for this kind of HPC workload here. You can see it's just a few files here, just 100. But it's just it's very huge. It's it's 10 terabyte to 100 terabyte. So we can saw this through output is very higher, and it's also a frequent I/O here. So this through output is about the 10 gigabyte per second. It's 10 gigabyte. It's not a BPS. It's a big. It's a capital B. So it's very huge through output necessary for this kind of workload load here. Okay, so we have about the 50 gigabyte reference data. So it has been reused frequently. So you can see we have lots of read and write through output here, and about 10 gigabyte per second. So we still need we still need some cache layer to reduce the backend reference data I/O. So after we use Alluxio here, we can put the reference data into the Alluxio layer. Then we can leverage this infrastructure to make sure it's just can have the compatible performance with existing infrastructure. Today, we have to put the reference data into the local disk, NVMe SSD. So it's need 1 gigabyte or 2 gigabytes per second to read. So today we can just put into the Alluxio, so we don't need a local disk anymore. Okay. So when we running this kind of the workload, so we have a couple of the best practices here. So if you have enough memory and SSD in the single node, so you just leverage the local first avoid eviction policy here. So it means you just avoid to switch data from memory to disk to memory. So using this approach for some ResNet, NiceNet 50, so you just have 143 gigabytes. You have sufficient memory and SSD on the local node, so you don't need you could leverage this eviction policy here, so you can speed up your processing rate. Okay, so if the data size, the training data size is huge than the whole cache, so it means so you have a sufficient media, you have sufficient storage to memory SSD to contain all the sample data. So it just keeps the default eviction policy. We have testing here. So you can see we have ResNet 50 here. So in the 170 iteration, so we just have the process rate is 191. But if the data size exceeded the pool size, so we can see significant downgrade for the processing rate here is a 45 iteration here. So it means so we saw a lot of the underlying file system block rate of file filling. So it's impact the processing rate. So now GPU is very expensive. So if we cannot use this GPU fully, use the GPU computation power, so it's just a waste of money. Okay. So we just changed the eviction policy here. So we can saw about just about a 10 image per second downgrade here. So it means if you have sufficient memory, so you just keep the eviction over here. Okay, let's take a look. So in the Kubernetes, we leverage the local volume host path for the SSD storage. So if using this approach, you can leverage the short circuits with local volume. So different pods can using the same host path to directly to access the data on the file system. So it will save some effort to access the gRPC socket. Okay, if training data is distributed in the Alluxio, the client do not to synchronize to local. It means so you just do some remote access to the data on the other node. So it just leverages the bandwidth of the network. Don't persist it. Okay. Today we already have a harm chart for Kubernetes for Alluxio, but it's not built. It's not native yet. So we can saw we don't have a sufficient health check for missing the liveness prop, readiness prop. So we need to prove it. Observability supported for Prometheus, it does not observe. So So for a file system, we need the file system report metric exporter. We need to know exactly what happened under this file system. We need some dashboard as well. For data layer cache, so we need some schedule awareness in the future as well. OK, so for the Alluxio Fuse, so we have a couple of the issues here. We can solve the performance downgrade during the eviction. We can solve it doesn't support the pan write or intensive write, so we need to improve it. For a couple of problems, so for Fuse, if we're using the Fuse in your existing workload, so you spend additional memory for the Fuse JVM. So we need to consider about it. So how can leverage the small bootstrap for the Fuse demo set and other demo set. So it's we also can solve this policy. So it's an eviction policy. We need some last recent used evictor, also last recent frequent used evictor to change the eviction policy for different workload. OK, the next takeaway. So if you have enough to catch in one machine, so you just avoid to swap data from disk to memory for your training workload. So you have the best performance for your training. If the sample data is huge and it's bigger than the whole cache, so you just keep eviction, default eviction, LRU, FU policy. OK, so for SSD tier, so if you have the data is already could not contain it in memory, so you're using the SSD tier, so you could use it as a short circuit to speed up the training process. For HPC, so we can leverage this read-only feature. Today, we don't have using the write feature. OK, for small node, you just disable the passive mode cache. For HPC, we always use for reference data just to keep the memory. OK, so in future we improve the schedule locality for MPI and PSNAP. That's all for today's talk. Thank you.